Okay, so last day we talked about acid-base reactions. We really only talked about one reaction. That was a neutralization reaction. As I mentioned, there are reactions that you've already witnessed in the past. We've witnessed how acids react with metals to produce hydrogen gas. We've also witnessed how acids react with carbonate. The carbonate we used was calcium carbonate, it's essentially chalk, and they will react to produce carbon dioxide. And the bases, they don't, right? So acids and bases, they are kind of opposites, but they're not like complete opposites. Some react with certain things and others don't react. But when you do put them together as an acid and a base, you do get a neutralization reaction, and that produces water and some kind of ionic compound. We call it a salt. All right. So now the last section here is on the origin of acids and bases. And well, actually, let's just go through this. There's no real exciting thing about this. Synthesis of an acid. When a nonmetal is combusted with oxygen, it produces an oxide of that particular element. We'll just call it a nonmetal oxide. So when anything reacts with oxygen, it produces an oxide. And we can burn metals to produce oxides. We can burn nonmetals. And they don't even have to burn. Like iron. If you leave just iron out in the air, it will slowly, eventually oxidize and form rust. It doesn't need any fire. Even this piece of magnesium here, this piece of magnesium is dull because the surface of it has already reacted with some oxygen. If I were to take a piece of sandpaper, I could shine it back up, but after a few days it would become dull again. So they would ultimately form oxides even without burning, so it doesn't have to be combusted. I'm going to heat these up in a moment and show you the reactions, and I'm going to combust them just because I want the combustion to happen fast. But they don't have to necessarily be burnt in order to form the oxide. They just have to react with oxygen. So when a nonmetal, any of these guys over here, reacts with oxygen to form the oxides, if you take that oxide, then you dissolve it in some water, you end up getting an acid. So that produces an acid. The word oxygen itself was proposed by Lavoisier. I've talked about Lavoisier. He was that chemist back in the 1700s that kind of organized the chemistry world. He came up with the law of conservation of mass, stating that in a chemical reaction, the mass of the reactants have to be equal to the mass of the product. That's why we balance chemical reactions. But he also came up with some more functional names for some of the elements. I probably told you this story, that oxygen, before it was named oxygen by Lavoisier, was sometimes called vital air because they did little experiments to determine that there was a part of the air that was vital for life. And I probably told you a story. Did I tell you the story how they tested that? They'd put a little bird like under a bell jar, seal it out from the air, and after a while the bird would fall over and die. And so they said, there must be something in the air that's really important for things to live. So they called it vital air. They tested this out they also knew that if you put a candle under a bell jar, sealed it out from the rest of the air, that the candle went out very quickly as well. They thought maybe that it was this vital air that was important for burning, the same as it is for keeping things alive. So then they took a bell jar and they put a little bird under the bell jar with a candle. Then the candle went out and the bird died a lot quicker. So they soon discovered that there was something in the air that was vital to life. So they called it vital air, all right? Now, there was all kinds of other different names that different chemists had given this vital air. But Lavoisier wanted to call it something that was more useful to chemistry. The prefix oxy comes from the Greek, and it means acid forming. It actually means sharp, all right? So oxy means sharp. And the idea of acids being sharp in that they could burn you, right? Or they have a sharp taste, right? They're very sour. So oxy means acid in Greek, and oxygen means something that generates acid. That's where the ending of many of these elements come from. Anything that ends in gen comes from the same word as to generate. So oxygen is an acid-forming element. Why? Because they knew if they took oxygen and allowed it to react with the nonmetals, and then you took that nonmetal and dissolved it in water, it formed acids. And so Lavoisier called it oxygen. Okay? Just on an aside, hydrogen comes from the fact that when you burn hydrogen with oxygen, you get water. The prefix hydro means water, right? So hydrogen is the gas that when burnt with oxygen forms water. So it's water generating. It's a water generating element. All right, so that's where some of these names came from. So oxygen is very important in forming acids, but they've later discovered that oxygen is important in forming bases as well. So let's put an example up here. So here we have the element carbon reacting with some oxygen to produce, what's it going to produce? What's the product going to be? Yep, carbon dioxide. And that one doesn't need to be balanced. It's balanced right there, right? So one atom of carbon gets together with a molecule of O2 to produce carbon dioxide. If we now take that carbon dioxide and we react it with water, those molecules get together to form H2CO3. H2CO3 is hydrogen bonded with a carbonate. All right, that's a carbonate. And so what do we call that acid when the hydrogens are added to carbonate? What does the name become? Carbonate turns into what name when we add H's to it and make it become an acid? What do we got? Carbonic or carbonic acid. And so that is carbonic acid. Now that second reaction right there, and I've already talked to you about this a little bit, I mentioned it, but that second reaction where you take carbon dioxide gas and get it to react with liquid water is what they do at the beverage manufacturing companies when they inject large amounts of carbon dioxide into the pop. That reacts with the water and produces carbonic acid. And that's why you have that kind of sour taste to it when you drink it back. And also why when you drink a pop very fast, it almost burns the back of your throat. You can kind of feel it at the back of your throat. And that's because there's a little bit of acid in there, all right? So that is the reaction that makes pop acidic. That's what gave it a pH of approximately 2 to 4, depending on what you guys measured the other day, all right? Now this reaction also happens naturally in the air. In a moment, I'm going to talk a little bit about something called acid rain. I asked you to read about it the other day. The air normally has carbon dioxide in it. That's a normal thing to be found in the air. And that means all water that's exposed to the air will have this reaction taking place. So that means a little bit of carbon dioxide will be dissolving in regular natural lake water or river water or even tap water, and it will produce a very small amount of carbonic acid, all right? So tap water tends to be a little acidic. Now, let's try it with this tap water. I think we tried it the other day. So there's some tap water. I'm going to put some bromethymol blue. What were the colors of bromethymol blue again? What was our acid color and our base color? Just to keep you ready for a test coming Thursday. Test coming Thursday. Just to freak you all out. Yep. Yeah, base blue, right? And yellow for acid. So let's see what we get here with our tap water. Put a few drops in it. And we started out with it being kind of a nice blue. Here, let's make sure I don't have a whole lot of anything on my scupula as I stir here. Actually, I can stir with a splint. I was going to use a splint in a moment, but I'm not going to. We'll give a little stir here. And what do we get there? We get a little bit of a kind of a turquoisey blue, right? So a little bit between that yellow and blue. Perfect in between yellow and blue would be nice green, but this is a turquoisey blue. This is probably indicating that it's a little more base. No, this might be the neutral color. Anyway, so that doesn't contain a whole lot of carbon dioxide, or actually it would be more yellow. We're going to generate some carbon dioxide here in a moment and see if we can make it become yellow. Actually, let's do that right now. So here's what I'm going to do. I'm going to get rid of this water. And I'm going to put a little bit of water in here, just a little bit. And I'm going to get my goggles on. Then I'm going to fire up the Bunsen burner, main gas on. Then we'll get the Bunsen burner going. That's fun. And on this piece of paper towel here, I've got 3 elements here. I've got carbon, non-metal, magnesium, metal, and then I've got sulfur, also non-metal. I'm going to save the sulfur for the end. So I'm going to take the carbon, and I've got a watch glass here, and I'm going to get this carbon to burn. See if we can get it to start burning. This is a piece of charcoal. There we're getting it red hot. It's burning a little bit. I maybe should have used a splint. We'll use this. This will work. So it's kind of burning. Now what I want to do is I want to catch the carbon dioxide that comes off of it. And oh, I should have tried this. Usually I put in some pure oxygen to get it to burn really well. I'm going to cheat a little bit. I'm going to add some air to this. So you can see it burning and glowing away. I'm hoping it's producing some carbon dioxide. Colorless gas, won't be able to see it. I'm going to drop it into the water. So there it extinguished it. There's a little bit of smoke in there. That's not what I'm worried about. But what I wanted to do was catch some of the carbon dioxide. And now what I want to do, hopefully this isn't too hot, I want to agitate this very carefully because I want some of that carbon dioxide to dissolve in the water. So I need the air to kind of make lots of contact with the water. So I want to agitate it well, and I'm going to try to do this without making a complete mess. Now let's put some bromethymol blue into this. A moment ago, that tap water was giving us a turquoisey color. Let's see what we get this time. I need a little more to see what's going on. What do you think? It's a little more green, isn't it? So a little more green means what? Acidic or basic? It's a little more acidic. Now carbonic acid is not a very strong acid, so it's not like I'm going to get it way down to a pH of 1. But we did get it to be a little more green. So that carbon dioxide that was produced by this burning carbon reacted with the water and produced a little bit of an acid. Not a really strong acid in any way, but still an acid. All right, so if I take a nonmetal and I have it react with oxygen to form an oxide, and I take that oxide and I dissolve it in water, then that will produce an acid. Synthesis of a base. Metals can react with oxygen. It's probably more common to think of metals reacting with oxygen, like rusting of iron. Form metal oxides. In a moment I'm going to burn some magnesium. I'm going to produce some magnesium oxide. And if we take those metal oxides and dissolve them in water, well, it turns out we get a base. It has everything to do with the way a metal hangs on to electrons versus a nonmetal. They have completely different attractions for electrons, which means they pull and they share atoms, electrons differently with the oxygen than they do the nonmetals. And you'll learn more about that as you continue on in chemistry. So when we have a metal oxide and it reacts with water, we end up with a base. Now, the example that is created in the note is reacting some potassium with oxygen, and that's pretty dangerous to burn some potassium and oxygen. So I'm going to use magnesium instead. It doesn't matter. It's still going to get the point across. And I do have the slide bring it up for us, but we should be able to do this type of thing. What is the product going to be? What is the product going to be? We should always be thinking ahead like that as chemists. What product will we get when potassium reacts with oxygen? Yep. Potassium oxide. So we need to get a formula for potassium oxide, which means we need to cross over the charge for potassium with the charge for oxygen, right? Again, that's all about doing chemistry. We're always thinking about what that formula will be. What will this formula be when we cross those charges over? I love the Tuesday after a long weekend. I have to have extra long waits to let you guys think. Yep, Megan, what do you got? Yep, K2O, excellent, K2O. And we should balance this up. Again, all those skills come into play, so we should always be thinking, what do we need to do to balance this? Because in a couple of days, there's going to be lots of balancing to do. It'll be fun for me. Megan, what do you got? 4K, 2K2O. I like it. And those are just the answers coming up, which is not a big deal. And when the K2O reacts with water, it's going to form a base. That means you should be able to tell me what the product is. Because if it's a base, it's got to have a certain part to this ionic compound. There's got to be a certain piece on there. That's what makes a base a base. So what must the product be? It's got to have this piece on the back end. That's what makes a base a base. What ion is it that makes a base a base? What do we need? Again, the Tuesday pause. What do you got, Marissa? Yeah, it's got to be potassium hydroxide, because it has to have a hydroxide on it. Bases have hydroxides, right? What would the formula for potassium hydroxide be? Yep. KOH. K, charge of 1, OH, charge of -1. Now we need to balance it. Oh, that's pretty ugly. Or is it that ugly? What am I missing? What do you got, Marissa? That's it? 2, 2, 2, 2. Wow. Much easier than I thought. I thought that was going to be a lot more work. 2, 2, 2, 2, 2. Good. I like it. Let me show you the magnesium reaction. Okay, so again, I'm going to do the same thing. I'm going to take some water, and I really don't need the watch glass for this, because when I burn the magnesium, it doesn't, the magnesium oxide is not a gas. It's not like carbon dioxide. It doesn't escape into the air. The magnesium oxide is the white ash that's formed when this burns. So the magnesium oxide isn't going to go anywhere, so I don't have to like kind of catch it in the container like I did that last one. So let's fire this up. I've got a pretty good length here, so you might not want to stare at the entire burning process, because as we know, it's fairly bright. So you could look away if you feel like to, because I'm going to look away, that's for sure, because it's a very bright piece. Let's get it burning here. Yeah, okay. Don't look at it. Look away. It's still burning. Holy cow, what kind of a piece did I get? That's exciting. So that's now out. And there's the white ash. I want to put it in there. Get it in there. Break off in there. I'm not going to put that little unburnt piece of magnesium there, because where I have the wire, there's an unburnt piece there. I'll just place that, but flick it all over the place. All right. So, same thing. I'm going to add some bromethymol blue. Actually, I should stir it up first, and then I'll add the bromethymol blue. Did I use that to stir something already? Oh, that was the neutral water that I stirred with that, right? It wasn't the acid water. Let's mix that up a little bit. Give it a good agitation here. It turns that magnesium oxide doesn't dissolve very well. You'll notice that the white powder is still there. But it does dissolve a little bit. Let's put a little bit of this in here. Put a second drop in there. Mix that up. Let's put another drop so we can see a little darker. What do you think? Did we get bluer? Right, that was my carbonic acid right there. That's my base. And the water, the plain water, I got to do one more here, but I can always dump it out. Plain water was a little bit green, right? Give that a little swirl. No lid on that. Yeah, that looks a little bluer, right? So we did turn that into a base, right? So there you can see it there in the middle. All right, excellent. So when metals, and they burn, they react with the water, they become a base. Potassium hydroxide, don't worry about the bottom part used in soaps, fertilizers, and paint removers. I'm not worried about that stuff. I'm making a mess here because I'm squeaking all the water on the floor. Okay? All right, so non-metals, burn them, dissolve them in water, you get acids. Metals, burn them, dissolve it in water, you get a base. Now, some stuff doesn't dissolve in water very well, all right? If you take iron and burn it and try to dissolve iron oxide in water, rust does not dissolve in water very well, all right? So you really don't get an acid or a base because it doesn't dissolve well. It still has the ability to be a base, but because it doesn't dissolve well in the water, it doesn't produce very much. All right, let's then talk a little bit about this acid rain. Pollutants that cause acid precipitation. What chemical process leads to this? When you burn fossil fuels, things like diesel fuel, gasoline not so much, coal. Coal contains a lot of sulfur impurities. That's what makes crude oil stinky. That's what gives petroleum that special smell on some of those mornings when the air is calm. It's the sulfur that's mixed with the fossil fuels. So when you burn the fossil fuels, you burn the diesel fuel or you burn the coal, not only does it produce carbon dioxide, but it also produces sulfur dioxide. That sulfur dioxide can react with oxygen that's already in the air to form sulfur trioxide. And that sulfur trioxide can react with the water, again in the air, and I'm going to put some things here. That's a gas. That's the liquid in the rain. That becomes aqueous. And what is that stuff called? What is it called when the hydrogens are added to a sulfate? Yep, Sammy? Sulfuric acid. Excellent. Sulfuric acid. The acid rain is not as big of a problem as it was in the 60s and 70s. All right, in the 60s and 70s, post-war, lots of kind of industrial work going on. We're burning coal to produce electricity. There's more fuel being needed to run vehicles. There's diesel engines that are being used to transport materials. All of these things are not just producing carbon dioxide, which is a greenhouse gas, which is a different problem, but they're producing a lot of sulfur oxides. Those sulfur oxides are mixing with the air to produce sulfur trioxide. which then ultimately reacts with water to produce acid rain. Down in Ohio, along the other side of Lake Erie, there were a lot of coal-burning power plants. And in the 70s and 80s, the prevailing winds would take that sulfur trioxide, it would head right over Lake Erie, and it would come right into southwestern Ontario. And this kind of stretch from Windsor up towards, Ottawa, and that had really heavy acid rain damage, right? The acids were reacting with plants, right, and causing damages on the surfaces of the plants, on the leaves, but they were also reacting with anything made of concrete. Concrete contains a carbonate, all right? Concrete contains a substance that is a carbonate, and as we saw, that if you have strong enough acid, it reacts with carbonate to produce carbon dioxide. So concrete structures were becoming pitted and were literally dissolving away because of the acid rain. So it was a problem. Now they've kind of got it under control. When they make diesel fuel, they've created a way to remove the sulfur out of the diesel fuel. So now when you've got a diesel engine, a big truck that's running away, that it doesn't produce as much sulfur oxides because they've removed the sulfur from it. Same with coal-burning power plants. They now can put something on the plant, a part of the structure, that is what we would call a scrubber, and it has the ability to remove some of the sulfur oxides, turn them into sulfur solid, and then remove that away and do something else with it. So they have had ways of removing the sulfur from those substances, and therefore reducing the amount of acid rain that's being produced. Let me burn the sulfur and show you this. Now this is stinky. This is stinky stuff. Just like I said, sulfur is a stinky molecule. I'm going to burn it here, and it might be so stinky I might have to move it across the way into the fume hood. But we'll see. We'll worry about that later. What's that? That's my carbon. That's fun. That's my magnesium. Let's get rid of this and just put some clean water in it. And this time, again, I have to catch the gas, because when sulfur burns, it produces sulfur dioxide gas, which is going to be stinky, which will be fun. And I've got to catch that gas, and then I got to kind of mix it in with the water. So I'm going to use a deflagrating spoon, because sulfur will melt. And if I have it in this as it's burning, it's going to melt and drip all over the place. So I'm going to put it in the deflagrating spoon, right, just like that little yellow piece, because that little yellow piece there is what sulfur looks like, right, yellow solid. And we're going to burn it, and we're going to get it to melt. And when it burns, it produces a nice little blue flame. It's very nice, but it's deceiving because it's stinky. Very stinky flame. That's a terrible lighter. Better. Okay. And this time I'm going to need a watch glass again, because I want to catch that gas. So I'm going to get everything set here. So we'll get this thing heating. Whoa, what was that? Spit out something. I got some dangerous mixtures here. Oh, I got some sugar in here. Uh-oh. Sugar and sulfur. I don't know what this is going to do. This could be dangerous. Sugar and sulfur. Oh, there we got the burning sulfur. That's nice. Put that in there. Put that on there. I'm going to let it burn. I can smell it. It stinks. Ah, terrible stuff. Woo! Do you smell it yet? Woo! It's good stuff. All right, how hot is it? Not too bad. I give it a mix. Make sure, just put my finger on the lip here so it doesn't come. Oh, that didn't work at all. Let's mix it up. I don't really normally do these demonstrations. That's why it's making such a mess. That's fun. Okay, so we've mixed it up there. Some smoke in there. Let's put some bromothymol blue in. Let's give it a swirl. Woo-hoo. Oh, terrible. What do we got? Yellow, nice and yellow. Sulfuric acid is a strong acid, much stronger than carbonic acid, right? We probably burnt about the same amount. Slightly acidic, far more acidic. And so there you can see there that the sulfuric acid definitely does that. And I'm going to dump this out over here. Do you want to? No? All right. Smells like rotten eggs? You don't smell anything? All right. It stinks right here, that's for sure. Okay. Last little note here, And then I give you the review, because you've already done some of the problems based on acid rain, because I assigned those the other day. In some places, when acid rain was really an issue, like I said, probably about 30 years ago, there were entire lakes that were dying, right? Fish were not able to survive in it, and aquatic plants weren't able to survive. And various methods were used to kind of rehabilitate the lake, to bring the life back, to decrease the pH. Sorry, increase the pH, to make it less acidic and more basic. So that means we got to bring the pH numbers up to 7. One method that was used was to take calcium oxide. They wouldn't have took a piece of calcium, went out there and started a campfire and burnt it. They would have actually just had calcium oxide powder and add it to the lakes, which then resulted in calcium hydroxide. And here you can see I've now got the calcium hydroxide with the sulfuric acid. And in the end, a neutralization reaction would take place. Calcium hydroxide isn't very soluble, so it's a good one to use because it will only kind of produce as much base as needed to dissolve or to react with the acid. So you would never go too far and make it basic, because it's a very weak base. So calcium hydroxide is not very basic. It dissolves a little bit. You wouldn't want to use sodium hydroxide. Sodium hydroxide dissolves really well. And if you dumped sodium hydroxide in it, you could run the risk of having too much of it be neutralized and then end up with a basic lake, which is just as bad as an acidic lake. So calcium hydroxide is a good one. It dissolves a little bit. It will neutralize what needs to be neutralized, but won't go overboard. It's not strong. It wouldn't turn it into a basic lake. Keep in mind that last reaction is an example of a neutralization reaction that we looked at the other day. Okay, and that brings us to the review, and you guys got a pretty good deal. Well, it's just all of them in the book. I just assign them all. Like, do them. Practice. It's a review. It's practice. I give you as much opportunity to practice as possible. You have the rest of today's class. That is looking like 40 minutes. And then you've got tomorrow's class also to review and ask questions, etc., etc. And the test then is on Thursday. Okay? It does. Stinks like sulfur. Stinky.